Astronomers don't usually build for a discovery before it happens. And yet, right now, they are. Infrastructure is being assembled with one purpose in mind: to catch 3I, Atlas's successor, not if it arrives, but when it arrives. The Vera C. Rubin Observatory will comb the sky, night after night, hunting fast-moving anomalies. Machine learning systems are being trained to flag objects that refuse to behave like comets. Detection pipelines are being tuned for something that isn't here yet, unless it already is. Because here's what no one wants to say out loud. If 3I was reconnaissance, then 4 won't bother hiding. Propulsion becomes impossible to deny. Geometry becomes too clean to excuse. Stay until the end to understand why confirmation may be closer than anyone is willing to admit. If these questions pull at you the way they pull at me, consider subscribing so you don't miss a single chapter as this story unfolds. Leave a comment telling me where you are in the world right now, what hour you're listening, and what you think 3I, Atlas's successor, might be. Part 1. The bet is already placed. Before 3I, Atlas, completes its journey toward Jupiter in 2026. Something unusual is happening in astronomy departments around the world. Scientists aren't only studying the object we have, they're modeling the one we don't have yet. They're building frameworks for an arrival that hasn't occurred. They are, quietly, placing bets on a successor. This marks a fundamental shift in how we treat interstellar visitors. For decades, these passers-by were theoretical curiosities, mathematical possibilities whispered in graduate seminars, then buried in appendix tables. Then, Oumuamua tumbled through our solar system in 2017, and everything changed. The universe handed us something we were not prepared to explain. 2 years later, Borisov arrived, and the floodgates of speculation opened a little wider. Now we have 3I Atlas, and the scientific community is no longer asking whether another will come. They're asking when, because astronomers have moved beyond object-by-object analysis into something far more revealing. Population-level forecasting. They are treating interstellar visitors not as isolated oddities, but as members of a statistical family. And the moment you start building models that predict frequency, density, arrival intervals, you reveal a very specific assumption. You assume these objects are common. You assume they follow patterns. And patterns, by their nature, can be recognized, analyzed, anticipated. The discovery of only 2 confirmed interstellar objects forced scientists to revise estimates of interstellar number density upward by orders of magnitude. Hold that thought, just for a moment. 2 data points were enough to rewrite our sense of how crowded the galaxy may be with wandering bodies. What happens when we have 10? What happens when we have 100? Enter the Vera C. Rubin Observatory. Set to begin operations soon, this facility will reshape everything we think we know about detection rates. Current surveys catch maybe 1 interstellar object every few years, if we're lucky. Rubin could detect them by the dozens, possibly by the hundreds. Not because more objects are suddenly arriving, but because we'll finally have eyes sharp enough to notice what has always been passing through. A higher discovery rate doesn't prove an artificial origin, but it does confirm something just as important. We have been flying blind. The question is no longer whether interstellar objects are rare. The question is what we do when we realize they never were. Commonality opens doors that rarity keeps sealed. When you have 1 strange object, you shrug and move on. When you have 10, you start hunting patterns. When you have 100, patterns become unavoidable. Already, quiet discussions are forming about clustering, arrival timing, velocity families. These are not conspiracy theories. They are legitimate statistical questions about whether these objects show correlations that randomness should not produce. And here is where the speculation becomes interesting, where the step from science to science fiction starts to feel less like a leap and more like a slow, careful stride. If 3I, Atlas, were engineered, if it were a probe designed by something not from here, would a successor be expected? Rationally speaking, yes. Exploration is never a single-shot endeavor. Reconnaissance demands repetition, confirmation, triangulation. 1 data point is an accident. 2 is a coincidence. 3 is a pattern. 4 is a mission. So what would that mission look like? Human exploration follows a rhythm. We sent Voyager to the outer planets. We sent New Horizons to Pluto. We sent Parker Solar Probe to kiss the sun's raw light. Each mission builds on the last. Each design evolves. Each objective sharpens. If an intelligence was surveying our solar system, why send the same probe twice? Why repeat a design that already served its purpose? That is the unspoken tension in the scientific community right now. If 3i is just a rock, then its successor is just another rock. And we catalogue it and move on. But if 3i is something else, if it represents intention rather than accident, then its successor becomes the most important object in human history. Because it won't be a repeat performance. It will be an escalation. And escalation means dropping pretense. It means moving from stealth to signal. It means the next object might not bother looking natural at all. You have to understand what is unfolding here. The bet is not that another interstellar object will arrive. The bet is already placed. The odds are calculated. The infrastructure is being built to detect it. What remains uncertain is not the arrival, but the reveal. Will the next visitor play by the same rules? Will it tumble and outgas and pretend to be a comet, or will it do something we cannot explain away? 3i, Atlas, may not be exploration. It may be reconnaissance. And reconnaissance, by definition, is never the final act. It is the setup. It is the advanced scout reporting back, saying the coast is clear, saying the system is mapped, saying the approach is viable. What comes next is not discovery. It is confirmation. And confirmation does not need to hide. Part 2. The successor problem. If 3i, Atlas is artificial, then repeating its design would be a mistake. In fact, it would be more than a mistake. It would be inefficient, redundant, strategically pointless, and intelligence, by definition, does not waste resources on redundancy without purpose. Look at how human probe lineages evolve. Voyager 1 and 2 were twins. Yes, but they were the last of their kind. New Horizons did not copy Voyager. It learned from it. Parker Solar Probe did not replicate earlier solar missions. It redefined them. Each generation of spacecraft represents not just incremental improvement, but fundamental redesign based on new objectives, new materials, new physics. The gap between Voyager and Parker isn't 30 years of tweaking. It is 30 years of transformation. Now apply that logic to interstellar probes. If an intelligence capable of crossing light years decided to send a second mission to our solar system, why would it send the same thing twice? It wouldn't, unless the first mission failed, unless data was lost, unless the objective was incomplete. There is no reason to duplicate. And if 3i, Atlas, is performing as intended, gathering data, transmitting results, then its successor would have a different job entirely. This is where military and surveillance evolution becomes instructive. First-generation reconnaissance is always about staying hidden. You want to observe without being observed. You want to collect data without triggering alarms. But second-generation reconnaissance operates under a different assumption. They already know you are there. So stealth stops being the priority. Performance becomes the priority. You stop hiding and start optimizing for speed, for coverage, for bandwidth. The progression is almost formulaic. Stealth, then performance, then intent. The first probe hides. The second probe performs. The third probe announces. And if we are watching this sequence play out right now, if 3i represents the stealth phase, then 4 represents the performance phase, which means it will not look like a comet. It will look like something we have no natural explanation for. Here is the problem with mimicry. It works best during first contact. Oumuamua confused us because we had never seen anything like it. Borisov reassured us because it behaved like what we expected. 3i, Atlas, sits somewhere in between, strange enough to provoke questions, familiar enough to allow explanations. But mimicry has diminishing returns. Once you know someone is watching, once you know they're searching for patterns, disguising yourself as the same thing over and over stops being clever. It starts being suspicious. Imagine receiving 3 letters over 3 years. The first has no return address and strange handwriting. You're curious, but cautious. The second has a fake return address and normal handwriting. You relax. The third has another fake return address. Now you're paying attention. You start noticing the postmarks. You start analyzing the ink. By the time the fourth letter arrives, mimicry doesn't help anymore. You're already looking for the pattern beneath the disguise. Observational pipelines are doing exactly this right now. They're searching for non-dusty hyperbolic objects. They're flagging outliers. They're training algorithms to recognize what doesn't fit. Current surveys are biased toward comet-like detections because comets are bright, active, easy to spot. But those biases are being corrected. New instruments don't need a coma to see you. They don't need outgassing to track you. They just need motion and reflectivity. And if the next object doesn't produce either in expected ways, that absence becomes the signal. So, what happens when the next interstellar object does not look natural at all? What happens when it moves too fast, reflects too uniformly, accelerates too precisely? What happens when every natural explanation requires statistical outliers stacked on statistical outliers? At some point, the simplest explanation stops being exotic physics and starts being engineering. This is the successor problem. If 3i is a probe, then 4 cannot be a copy. It has to be an evolution, and evolution means shedding the disguise. It means prioritizing function over camouflage. It means accepting that discovery is inevitable and optimizing for what comes after discovery, not what comes before. The question is not whether another interstellar object will arrive. The question is whether it will still be pretending. Part 3. Dropping the comet mask. Camouflage works once, maybe twice if you're lucky. But repetition turns camouflage into a calling card. And right now, interstellar objects are running out of places to hide. When Oumuamua arrived in 2017, its lack of a coma caused genuine confusion. Comets have tails. Asteroids don't tumble quite like that. It occupied an uncomfortable middle ground, neither one thing nor another, and astronomers scrambled to fit it into existing categories. Eventually, they settled on calling it an interstellar asteroid, even though its behavior suggested otherwise. The important part is not what they called it. The important part is that they expected a coma and did not get one. Expectation mismatch is always revealing. Borisov, by contrast, behaved exactly like a comet. It outgassed. It developed a tail. It followed predictable trajectories. Scientists breathed a sigh of relief. Finally, something normal. Finally, something we understand. Borisov was the reassurance we needed after Oumuamua unsettled us. It told us the universe still made sense. Then came Dry Eye, Atlas. Dusty, tumbling, faintly active, not quite as strange as Oumuamua. Not quite as normal as Borisov, sitting in that awkward middle zone where questions outnumber answers, but not by enough to force a reckoning. And this is where the mask metaphor becomes useful. If these objects were deliberately designed to mimic natural bodies, 3i, Atlas, represents the point where the disguise starts showing seams. But here is what has changed since 2017. We are not just passively observing anymore, we're actively hunting. Machine learning classifiers are now trained to flag outliers before human astronomers even see them. These algorithms don't care about your preconceptions. They don't care what something should be. Comet, asteroid, either way. They compare data to patterns and highlight what doesn't fit. And increasingly, they're finding fast movers that defy classification. Objects appear in survey logs, get flagged as anomalous, then disappear before follow-up can be scheduled. Are these objects artificial? Probably not. Most are likely data artifacts, instrument glitches, or genuinely unusual natural objects. But the point is that observational saturation is happening. We are reaching a threshold where hiding as a comet becomes harder and harder because our instruments are getting better at distinguishing genuine cometary behavior from something that only looks comet-like from far away. Think about what a comet actually is. Dirty ice. When it gets close to the sun, that ice sublimates, creating a coma and a tail. The sublimation process is messy, asymmetric, and produces non-gravitational accelerations as gas jets push the nucleus around. This is well understood physics. We can model it. We can predict it. And that means we can recognize when something is pretending. A probe mimicking a comet would need to reproduce all of these effects convincingly. It would need to outgas at the right rate, in the right directions, with the right spectroscopic signatures. It would need to tumble in ways that match natural rotation induced by asymmetric outgassing. It would need to leave a trail of debris chemically consistent with solar system formation. This is not impossible, but it is complicated. And the more we observe, the harder it becomes to fake. So why bother if you are an intelligence sending a second probe to a solar system that has already detected your first? Why continue the charade? Camouflage made sense when discovery was uncertain, but discovery is no longer uncertain. We're looking, we're watching, we're waiting. At this point, camouflage stops being protective and starts being performative. This is where deliberate visibility becomes interesting. What if the next object wants to be seen, not as a threat, not as an invasion, but as a signal, a way of saying, yes, we are here, and yes, we are intentional. Humans have tried this. 2. We sent the Arecibo message into space in 1974. We attached plaques to Pioneer 10 and 11. We loaded Voyager with golden records. These were not scientific instruments. They were signals. They were attempts to say, if you find this. No, we made it on purpose. What if 3i is the same kind of gesture? What if it isn't trying to hide, but trying to communicate through its very existence? You don't need to broadcast a message if your presence is the message. You don't need to transmit data if your trajectory, your velocity, your material composition scream intention loud enough that even cautious scientists cannot ignore it. The mask is getting heavy, the disguise is wearing thin, and the next object to enter our solar system might decide that pretending to be natural is no longer worth the effort. Part 4. The velocity wall. There is a speed beyond which nature struggles to explain itself, not because physics breaks down, but because the statistics do. And we are approaching that threshold faster than most people realize. Hyperbolic excess velocity is a straightforward concept once you strip away the jargon. Every object in our solar system is gravitationally bound to the sun. It orbits, it returns, it follows elliptical paths. But interstellar objects are not bound to the sun. They are simply passing through. Their trajectories are hyperbolic, meaning they come in, swing around, and leave forever. Excess velocity is how fast they move relative to the sun after subtracting the sun's gravitational influence. For most interstellar objects, this excess velocity should be modest. A few kilometers per second, maybe 10, maybe 20 at most. Why? Because these objects were presumably ejected from other star systems through natural processes. Stellar encounters can fling objects into interstellar space. Oort cloud stripping can do the same. But these mechanisms have limits. They can only accelerate objects so much before the physics stops cooperating. You need extraordinary circumstances to produce extraordinary speeds. Oumuamua had an excess velocity of about 26 kilometers per second. Unusual, but not impossible. Borisov clocked in around 32 kilometers per second. Also unusual, also not impossible. 3i, Atlas, is moving faster. Not absurdly faster, but enough to push the envelope of what random ejection typically produces. And here is the thing about statistical tales. The farther out you go, the less likely natural explanations become. Not impossible, just less likely. But speed is only part of the equation. The real eyebrow raiser is non-gravitational acceleration. This is when an object speeds up or changes direction in ways gravity alone cannot explain. For comets, this is normal. Outgassing produces thrust. Gas jets act like tiny rocket engines, pushing the nucleus around. We see it all the time. It is predictable, measurable, entirely natural. Oumuamua also exhibited non-gravitational acceleration, but it did not have a coma. It did not show signs of outgassing. So where was the thrust coming from? Scientists proposed several explanations. Maybe it was outgassing hydrogen. Maybe it was shedding surface layers. Maybe it was shaped like a pancake, and solar radiation pressure was pushing it. All plausible, all untestable, because the object left our observational range before we could confirm anything. But here is what makes scientists nervous. When non-gravitational acceleration aligns with the velocity vector, when it pushes the object in exactly the direction it is already moving, that starts looking less like random outgassing and more like propulsion. Random gas jets spray in all directions. Propulsion systems optimize thrust along the direction of travel. The difference is intent. Now introduce light sail physics. A light sail is exactly what it sounds like. A large reflective surface that catches photons from a star and uses radiation pressure to accelerate. This is not science fiction. This is established physics. Breakthrough Starshot is planning to use light sails to send tiny probes toward Alpha Centauri at a fraction of light speed. The concept works. The engineering is hard, but the physics is sound. And here is the thing about light sails. They produce acceleration profiles that look a lot like what Oumuamua displayed. Continuous low-level thrust aligned with the velocity vector. No outgassing required, no chemical propellant needed, just a reflective surface and a nearby star. If you wanted to design an interstellar probe that could navigate our solar system using only sunlight, a light sail would be an obvious choice. Does this mean Oumuamua was a light sail? No. It means a light sail could explain the observations without invoking exotic physics or improbable outgassing scenarios. It means the simplest engineering solution can fit the data better than some of the natural explanations we have been forced to construct. Now imagine 4 arrives moving at 50 kilometers per second, or 70, or 100. At some point, you run out of natural ejection mechanisms that can produce those speeds. At some point, you have to ask whether the object brought its own propulsion. And if it brought its own propulsion, it brought intention. And if it brought intention, we are no longer talking about rocks. Higher speeds also reduce the plausibility of random detection. If interstellar objects are rare and most move slowly, detecting a fast one by chance is unlikely. But if we start detecting multiple fast objects, if they keep showing up in our surveys, moving at speeds natural processes struggle to produce, then randomness stops being satisfying. Patterns emerge, and patterns demand explanations. The Vera C. Rubin Observatory will be particularly sensitive to fast-moving objects. Its wide field of view and rapid survey cadence mean it will catch things current telescopes miss entirely. If there is a population of high-velocity interstellar objects passing through our solar system, Rubin will find them. And when it does, we will have to confront an uncomfortable question. Why are so many of them moving so fast? At some point, propulsion stops being deniable. At some point, the velocity wall becomes a declaration. Part 5. Jupiter was not a coincidence. Jupiter is not just a planet. It is a gravitational switchboard, a navigation hub, a cosmic intersection where trajectories get redirected, velocities get amplified, and missions get adjusted. And if dry eye, Atlas is a probe. Its encounter with Jupiter in 2026 is not a flyby. It is an appointment. Let me explain why Jupiter matters. Our solar system is shaped by its gravity. Jupiter is so massive, so dominant, that for billions of years it has flung comets, redirected asteroids, and decided what stays in the inner system and what gets ejected into interstellar space. It acts as a gravitational shield for Earth, sweeping up potential impactors before they reach us. It also acts as a gravitational slingshot, accelerating objects to escape velocity with nothing more than a close encounter. Gravity assists are not magic. They are orbital mechanics. When a spacecraft approaches a planet on a specific trajectory, the planet's gravity pulls it in, curves its path, and flings it out again. If the geometry is right, the spacecraft exits moving faster than it entered. NASA has used this technique for decades. Voyager, Cassini, New Horizons all used Jupiter gravity assists to reach their destinations. You do not fight gravity, you use it. Now imagine you're designing an interstellar probe. You want it to survey our solar system, but you also want it to adjust its course based on what it finds. Maybe you need to visit a different region. Maybe you need to slow down for better observations. Maybe you need to speed up to make a scheduled rendezvous. You could carry fuel, but fuel is mass, and mass is expensive when you are crossing light years. Or you could use the solar system itself as your propulsion system. You could use Jupiter. This is where the difference between a flyby and a synchronization maneuver becomes critical. A random object passing through the solar system does not care about Jupiter. It might encounter the planet by chance, get deflected, and continue on an altered trajectory. But if an object is intentionally targeting Jupiter, if its approach geometry is optimized for a specific gravitational outcome, that stops looking random. That starts looking like navigation. 3I, Atlas, is heading toward a close encounter with Jupiter, not grazing it, not barely missing it. A close, optimized approach that will significantly alter its trajectory. Now, this could be coincidence. Interstellar objects cross paths with planets all the time. But consider the alternative. Consider that 3I planned this encounter. Consider that it needed Jupiter to adjust its velocity, to refine its orbit, to position itself for whatever comes next. Data exchange does not require landing. It does not require physical contact. If 3I is transmitting information, it could be doing so to a receiver positioned elsewhere in the solar system, or it could be updating its programming based on new observations, or it could be synchronizing with another probe, coordinating arrival windows, ensuring that 4I enters the solar system at the right time, on the right trajectory, with the right velocity. Timing windows are everything in orbital mechanics. If you want two spacecraft to meet, you cannot just launch them whenever you feel like it. You have to calculate transfer orbits. You have to account for gravitational influences. You have to ensure they arrive at the same place at the same time. This is hard enough within one solar system. Across interstellar distances, it requires precision that borders on absurd, unless, of course, you are using gravitational assists to fine-tune arrival. What if repeat visitors share encounter geometries? What if every probe sent to our solar system uses Jupiter as a navigation checkpoint? You would expect similar approach angles, similar perihelion distances, similar exit velocities. You would expect a family resemblance in their orbits. And if we start detecting that family resemblance, if 4I shows up on a trajectory eerily similar to 3I, then coincidence stops being a viable explanation. Here is the speculative leap. The idea that sounds absurd until you think about it for more than 5 seconds. What if Jupiter is not just a gravity well? What if it is a relay hub? What if probes have been using it for exactly this purpose for longer than we have been watching? You do not need to build infrastructure. You only need to recognize that a gas giant in the outer solar system is a perfect place to coordinate arrivals, exchange data, adjust trajectories, without ever getting close to the inner planets, where detection is more likely. This reframes everything. 3I, Atlas's encounter with Jupiter, is not a visit. It is a handshake, a confirmation, a synchronization event. And if that is true, then we are not watching a solitary explorer passing through. We are watching a network node checking in. And networks, by definition, are never alone. Part 6. Light sails. The simplest escalation. If you want to cross interstellar space without carrying fuel, you need a sail. Not the cloth kind, the photon kind. And the beautiful thing about light sails is that they are not exotic. They are efficient. Let me strip this down to basics. Propulsion is a momentum problem. Rockets work by throwing mass backward, and that recoil drives the rocket forward. It works, but it's costly, because you must carry all that mass with you. The faster you want to go, the more fuel you need. The more fuel you need, the heavier you become. The heavier you become, the more fuel you need to accelerate that fuel. It's a tyranny of diminishing returns, a loop that tightens the harder you push. Light sails skip the loop entirely. Instead of carrying propellant, you carry a reflective surface. Photons from a star strike the sail and transfer momentum. Each photon carries almost none, but there are trillions of them. Over time, that accumulated pressure accelerates the sail to astonishing speeds. No fuel tanks, no combustion, no exhaust. Just sunlight and physics. And this isn't theoretical. Breakthrough Starshot, a legitimate scientific initiative backed by serious funding and serious physicists, is developing light sail technology to send gram-scale probes to Alpha Centauri at 20% of light speed. 20%. Fast enough to reach our nearest stellar neighbor in roughly 20 years. If humans can engineer this with today's tools, imagine what a civilization 1,000 years ahead could accomplish. Now imagine 4I arrives as a light sail. What would we notice? First, reflectivity. Sails must be highly reflective to maximize photon momentum transfer. That means they could appear unnaturally bright for their size. with unusual phase curves as they tumble or orient. Natural objects absorb most of the light that hits them. Sails reflect it. That difference is measurable. Second, polarization. Light reflected off a structured surface carries polarization properties that differ from light scattered by a rough, natural body. Astronomers already use polarization to study asteroids and comets. A light sail could produce polarization signatures we have never seen in a natural object. Third, geometry. Sails need to be large and thin to maximize area while minimizing mass. So they might look stretched, elongated, possibly even flat. Oumuamua's strange tumbling and elongated shape sparked endless speculation. What if it wasn't an elongated rock at all, but a thin, reflective surface, tumbling end over end? Here's the catch, with sailing through interstellar space. Though, dust. The interstellar medium isn't empty. It's filled with microscopic particles, hydrogen atoms, trace molecules, across light years. Those impacts add up. They pit surfaces. They reduce reflectivity. They punch holes. A pristine sail leaving its home system might reach ours battered, pockmarked, and far less efficient, unless the sail is disposable, meant to be used once, discarded, and replaced. Modular sail systems could function like staged rockets. Use one sail to accelerate out of your home system. Jettison it. Deploy a new sail for cruising. Jettison that too. Deploy a final sail for deceleration and navigation inside the target system. That would explain why we might see damaged or fragmenting light sails. They aren't failures. They're spent stages. Compare sail shapes to natural fragments. Asteroids are lumpy, irregular, shaped by billions of years of collisions. Comets are dirty snowballs with asymmetric nuclei. Both tumble chaotically because their mass is unevenly distributed. A sail, even a damaged one, would tumble differently. Its mass is spread across a surface, not concentrated in a volume. Its rotation would be smoother, more predictable, less erratic. Light sails solve the speed problem cleanly. They explain how objects could cross interstellar space without massive fuel reserves. They explain non-gravitational acceleration without invoking outgassing. They explain unusual brightness and reflectivity without requiring exotic materials. And they stay entirely within known physics. No faster-than-light travel, no warp drives, no hand-waving, just engineering. If 4i arrives as a light sail, we'll know. Not instantly. Maybe not from a single observation, but the data will stack up. Reflectivity will look wrong. Polarization won't match natural predictions. Trajectory adjustments will align too perfectly with solar radiation pressure. At some point, the simplest explanation will stop being a weird rock and start being a sail. And once we confirm one light sail, we have to ask how many others pass through undetected, simply because we weren't looking for them. Part 7. Structured probes and the von Neumann taboo. Self-replication is the most efficient idea humans simultaneously understand and fear. And that fear, more than any technical limit, is why we avoid discussing it seriously. But efficiency doesn't care about fear. Let me say this neutrally. If you want to explore a galaxy with hundreds of billions of stars, you have two options. Option 1. Build trillions of probes and launch them all from a single origin point. That demands resource extraction on a civilizational scale, sustained industrial output for millennia, and launch infrastructure we can barely imagine. Option 2. Build a few dozen self-replicating probes and let them multiply as they explore. The math isn't subtle. Self-replication reduces launch cost by orders of magnitude. You send out a probe. It reaches a star system. It gathers local resources, builds copies of itself, and sends those copies onward. Exponential growth does the rest. Within 1 million years, an absurdly short time on galactic scales, every star system in the galaxy could be visited. This isn't speculation. It's applied mathematics. But replication does not equal invasion. That conflation is where human anxiety distorts rational analysis. A self-replicating probe is not a grey goo nightmare. It's not a locust swarm. It's an exploration strategy. Build, survey, transmit data, repeat. There's no reason to assume aggressive expansion or consumption beyond what replication requires. Fear of von Neumann probes says more about human psychology than probable alien behavior. So what would a factory probe look like observationally? First, infrastructure. You can't build copies of yourself without raw materials and energy. That means mining asteroids, processing regolith, extracting metals and volatiles. Those activities leave traces, waste heat, debris fields, spectroscopic signatures of industrial chemistry. Even a modest replication facility could be detectable if we knew where to look. Second, time. Replication isn't instantaneous. A probe arriving in our solar system might need years, maybe decades, to survey resources, to establish manufacturing, and produce offspring. During that window, it would be vulnerable to detection. It would need to park somewhere stable. It would need to run machinery. It would need to test systems. All of that produces signals. Third, multiplicative evidence. If self-replicating probes exist on galactic timescales, we shouldn't see one. We should see many, not all at once. But over time, the arrival rate would rise as the population grows. Early visits would be sparse. Later visits would accelerate. If we're detecting interstellar objects more frequently now than in previous decades, that could mean we're entering an era of increased probe traffic. Here is the uncomfortable truth. Even non-replicating probes leave traces, communication relays, observation posts, data caches. If an intelligence sends probes to multiple star systems, it needs a way to aggregate findings. That means leaving equipment behind. And equipment, no matter how well made, eventually becomes detectable. One confirmed probe recontextualizes everything. If we confirm even a single interstellar object is artificial, the statistical likelihood of others skyrockets. Because if one civilization developed interstellar probe technology, why would it be the only one? The galaxy is old. Stars have been forming, evolving, and dying for billions of years. If technological civilizations arise even occasionally and build probes even once, the cumulative result is a galaxy seeded with wandering machines. This is where fear melts into probability. We're not talking pure hypotheticals anymore. We're asking whether we already live in a galaxy where this happened long ago. Whether the objects we call asteroids and comets include a fraction that never formed in our solar system, whether our surveys have been cataloguing both natural debris and artificial visitors without knowing how to tell them apart. The von Neumann taboo exists because self-replication challenges human exceptionalism. It suggests the galaxy might already be explored, mapped, monitored. It suggests we are not the first intelligence to ask these questions, and it suggests the evidence might already be here, in our asteroid belt, in our Kuiper belt, in objects we dismiss as unremarkable because we haven't learned how to recognize the remarkable. What if we are not seeing the first probe? What if we're seeing the latest iteration in a lineage that began long before humans existed? Part 8. The Relay Hypothesis. Exploration is meaningless without communication. You can gather all the data in the universe, but if you can't transmit it home, you've accomplished nothing. And transmission across interstellar distances is not simple. It requires infrastructure. It requires relays. Think about how humans explore. We send rovers to Mars. Those rovers don't talk directly to mission control. They relay data through orbiters. Those orbiters aggregate information and transmit to Earth during optimal windows. That architecture isn't optional. It's necessary. Direct communication from a rover to Earth would demand enormous power and perfect line of sight. Relays solve both problems. Now scale that to interstellar distances. A probe exploring our solar system collects terabytes of information. Planetary compositions, orbital mechanics, atmospheric spectra, magnetic field data, maybe even biosignatures if it gets lucky. But sending that across light years requires either absurd power output or a relay network. Absurd power attracts attention. Relay networks don't. Passive relays are the elegant solution. Small, simple devices that receive data, store it, and retransmit when conditions are favorable. They don't need sophisticated AI. They don't need complex maneuvering. They just need to park in stable orbits and wait. A passive relay in the outer solar system could collect data from multiple probes, compress it, and beam it toward the origin civilization using narrowband transmission during optimal alignment windows. What would a passive relay look like? Probably nothing remarkable. A small, inert object in a stable orbit. No outgassing, no tumbling, no obvious thermal signature. It would look dead to our instruments unless we specifically targeted it with active radar. And why would we? We barely track the millions of objects already catalogued. One more silent rock could go unnoticed indefinitely. But active relays are different. They require power, maneuvering, maybe propulsion, to maintain optimal positioning. An active relay might adjust its orbit to maximize communication windows. It might orient toward incoming probes to receive transmissions. Those actions create detectable signatures, trajectory changes, thermal emissions, radio signals. If we're lucky. Now consider the architecture. 3i collects data. Quattri transmits it. That division of labor makes operational sense. The collector probe optimizes for stealth and observation. It minimizes energy use, avoids detection, and focuses on acquisition. The transmission probe optimizes for bandwidth and power. It doesn't need to hide. It just needs to relay the collected data back home, then continue to the next system. Bandwidth constraints over interstellar distances are brutal. Light takes years to cross even nearby stellar neighborhoods. A probe can't wait years for instructions. It must operate autonomously, decide locally, and batch transmit findings when windows open. That means long-term storage, compression algorithms, prioritization protocols that decide what gets sent first and what waits. Delay-tolerant networking is an established field in computer science, built for environments where communication is intermittent and latency is minutes or hours instead of milliseconds. Interstellar communication pushes this to the extreme. Messages take years to arrive. Responses take years to return. Entire missions execute based on instructions sent before the probe even launched. Relays create buffer zones. A relay in our solar system receives data from 3i, stores it, waits for optimal transmission windows, and sends it home in compressed bursts. Meanwhile, it receives updated instructions from home and queues them for delivery when the next probe arrives. This asynchronous architecture enables coordinated exploration despite vast distance and light speed delay. Why would relays prioritize stability over stealth? Because stealth is temporary. Eventually, any active system is detected, but stability can be permanent. A relay at a Lagrange point, in a stable Trojan orbit, or out in the Kuiper belt, could operate for centuries with minimal adjustments. It doesn't need to hide if it is patient. It only needs to avoid drawing attention until its mission is complete. And here is the final piece. Infrastructure outlives explorers. Human spacecraft die. Batteries drain. Systems fail. But the communications infrastructure we build, relay satellites, deep space networks, protocols and standards, persists. It gets upgraded, expanded, repurposed. It becomes the foundation for the next generation of exploration. If an intelligence has explored the galaxy for millennia, its relay network could be ancient, vast, and remarkably resilient. Individual probes come and go, relays endure, and if our solar system is a node in that network, if 3i and 4i are simply the latest visitors checking in, then somewhere in our outer solar system is a relay we haven't recognized yet. Waiting. Part 9. Probability, not proof. Statistics don't care about comfort. They don't care about skepticism. They don't care if the implications unsettle you. They care about numbers, and the numbers are starting to tell a story. Interstellar object density estimates are straightforward once you understand what they measure. How many objects per cubic parsec wander between stars? Before Oumuamua, that number was theoretical, extrapolated from models of system formation and stellar encounters. After Oumuamua, we revised upward. After Borisov, we revised again. After 3i, we revise again. Each discovery increases expected counts, because each discovery proves earlier estimates were too conservative. That's how science works. You build models from limited data. You make predictions. You test predictions with observations. When observations disagree, you update the model. The interstellar object density model has been updated 3 times in 7 years. That's not science failing. That's science operating exactly as designed. But here's where probability becomes uncomfortable. Single anomalies are easy to dismiss. Coincidences happen. Outliers exist, but repeated anomalies are harder to ignore. When the same kind of strange event keeps happening, when objects arrive with properties that push natural explanations to the edge, probability forces us to consider alternatives. Imagine flipping a coin 10 times and getting heads every time. Possible sure. The probability is about 0. Bifengi. Unlikely, but not impossible. Now flip that coin 100 times and get heads every time. The probability collapses to effectively 0. At some point, you stop calling it luck and start suspecting a weighted coin. Interstellar objects aren't coin flips, but the logic holds. One fast mover with odd acceleration, you shrug. 5. You question your models. 20. You question whether they're all natural. Frequency turns anomalies into patterns. Patterns demand explanations. Fleet probability is where this becomes mathematically interesting. If interstellar objects are randomly distributed, arrival times at our solar system should follow a Poisson distribution. Independent, memoryless, random. But if we begin to see clustering, if objects arrive in groups separated by long silences that deviate from randomness, that hints at coordination, extraordinary evidence scales with frequency. One interstellar object needs ordinary explanations. 10 require better explanations. 100 require extraordinary explanations if they share unusual properties. This isn't about impossible standards of proof. It's about cumulative weight. Bayesian updating gives us the framework. You start with a prior, your initial estimate of how likely a hypothesis is. New evidence arrives. You update probability based on how well that evidence fits each hypothesis. Each observation shifts the odds. If evidence repeatedly supports one hypothesis over others, it becomes more credible over time, even if no single data point is definitive. Apply that to interstellar probes. Before Oumuamua, the prior probability of artificial interstellar objects was essentially 0. After Oumuamua, it rose slightly because the observations were odd. After Borisov, it fell because Borisov looked normal. After 3I, it rises again because 3I strains natural explanations. Each object updates the probability. None alone is proof, but together they shift likelihood. Absence of proof is temporary. We've only been seriously searching for interstellar objects for a decade. Detection capabilities have improved dramatically in that time. The Vera C. Rubin Observatory will push them further. What we haven't detected yet doesn't mean we won't detect soon. Absence of evidence becomes evidence of absence only after a thorough search. We have not searched thoroughly. We have barely begun. Thresholds are being crossed right now. Instruments that couldn't see faint. Fast movers 5 years ago can see them today. Algorithms that once couldn't separate unusual trajectories from artifacts can do it now. The bar for confirming an artificial object drops as capability rises. We're approaching a point where unambiguous detection becomes not just possible, but likely. Here is the uncomfortable mathematical reality. If even 1% of interstellar objects are artificial, and we detect hundreds over the next decade, we should expect confirmation within years. If % are artificial, confirmation could come within months. The numbers are unforgiving. The more we look, the harder it becomes to avoid what's there. Patterns force explanations, and the pattern is already forming. We just haven't acknowledged it yet. Part 10. Why disclosure would lag discovery. Humans are slower than telescopes. Instruments gather data at light speed. Bureaucracies process implications at institutional speed. And that gap between detection and acknowledgement is where reality gets messy. Institutional conservatism in science isn't a flaw, it's a feature. Science advances through skepticism, reproducibility, peer review, Extraordinary claims demand extraordinary evidence because reputations, funding, and credibility are on the line. If you announce artificial interstellar objects and you're wrong, your career ends. If you're right but can't prove it conclusively, your career can still end. So, caution is the safest path. Reputational risk shapes what scientists say publicly versus privately. In private, astronomers speculate freely about Oumuamua, unusual accelerations, objects that don't fit models. In papers, that same speculation gets hedged. Qualified. Buried under technical language. This isn't dishonesty, it's survival. History offers a lesson. Pulsars were discovered in 1967. Jocelyn Bell initially considered artificial signals because the regularity was so precise. The nickname LGM-1 meant little green men, but publicly, that idea was minimized until natural explanations were confirmed. The discovery was revolutionary, yet acceptance took time, careful analysis, and reproducible observations. Ambiguity is safer than clarity. If an object shows unusual properties, scientists can publish measurements without declaring artificiality. They can present data, note anomalies, request more study, and avoid career-ending claims. That's rational behavior in a system where being wrong about something extraordinary is professionally catastrophic. Instrument error is the default explanation for anomalies. Telescopes fail, software glitches, calibration drifts. Before concluding something is truly unusual, you must rule out every instrumental and procedural explanation. That takes time, sometimes years, and if the object leaves observational range before you finish, you're left with haunting data and no follow-up. Now, add the complication of defense versus civilian pipelines. Military and intelligence agencies run space surveillance networks that track objects civilian astronomers never see. Those networks are classified. Their capabilities are classified. Their detections are classified. If a military sensor records clearly artificial behavior, that data doesn't get published in Nature. It gets stored in a secure system, analyzed by people who will never speak publicly. Confirmation requires redundancy. One observation isn't enough. 2 from the same instrument are better, still questionable. 3 from independent instruments using different methods is the minimum for real confidence. But coordinating multiple observations of a fast-moving transient is difficult. By the time you schedule follow-ups, the object may be gone. So how long could acknowledgement be delayed? Years, easily. Data is collected, analyzed, written up, submitted, revised, resubmitted, then published. That process often takes 2 to 3 years for uncontroversial results. For controversial results, longer. Add institutional caution, reputational risk, and the challenge of reproducibility. And a 5-year gap between detection and public acknowledgement becomes plausible. Media framing adds another delay. If scientists announce an artificial interstellar object, coverage will be sensational, speculative, distorted. That pressure encourages waiting until alternatives are exhausted. Scientists don't want to trigger panic, conspiracies, misunderstandings. So they wait, hedge, qualify, consider a scenario. An object is detected in 2024 with properties consistent with artificial origin. Initial analysis happens quietly. Findings circulate within a small group under non-disclosure agreements. Follow-ups are attempted, but the object leaves range. Data is analyzed for years. Papers are drafted, revised, submitted. Peer review raises questions. More analysis follows. By 2029, a carefully worded paper appears, noting unusual properties and hinting at artificiality without declaring it. By the time the public hears maybe, it could already be old news. The object was detected 5 years earlier. Those with classified access knew earlier still, and the object itself passed through long before that. This isn't conspiracy, it's bureaucracy, and bureaucracy moves slowly. Part owns. AI is already finding things we don't understand. Machine learning doesn't sleep. It doesn't get bored. It doesn't ignore patterns because they feel implausible. It processes, compares, flags, anomalies, and increasingly, it flags things we can't explain. AI-based anomaly detection begins by defining normal. You feed an algorithm thousands of examples: asteroids, comets, satellite glints, instrumental artifacts. It learns the patterns, then you give it new observations and ask, does this match what you've seen? If the answer is no, it flags the object. Black box classifiers are unsettling because they work without explaining themselves. Neural networks trained on astronomical data can be remarkably accurate, but they can't always tell you why they classified something the way they did. They learn correlations invisible to human inspection. That power comes with opacity. When a classifier flags an object as anomalous, we often don't know what feature triggered it. That creates a trust problem. If an AI says an object is unusual but can't explain why, do you follow up? Do you allocate telescope time to a possible artifact? Do you publish a result you can't fully interpret? AI flags, patterns, humans miss. That isn't speculative. It's demonstrated. Astronomers have used machine learning to discover new classes of variable stars, identify exoplanets in previously reviewed data, detect gravitational lenses, visual inspection missed. Algorithms outperform humans at certain kinds of pattern recognition. They're faster, more consistent, less vulnerable to cognitive bias. But interpretability is the price. We can train a network to classify with 99% accuracy and still struggle to extract the rules it learned. That matters when the question is artificiality, because we need to know what makes something different. Is it velocity, reflectivity, trajectory, spectroscopy without interpretability? We have detection without understanding. Compare this to filtering challenges in SETI. SETI processes enormous volumes of radio data searching for narrowband signals that might indicate technology. Most signals are terrestrial interference. Some are natural astrophysical phenomena. A tiny fraction remain unexplained. AI helps remove obvious false positives, but it can't definitively identify true positives because we don't know what a true positive must look like. Interstellar object detection faces the same problem. We know what natural objects look like. We think we know what artificial objects might look like, but we don't know what they definitively look like. So when an algorithm flags an object as anomalous, we're left guessing: genuine novelty, or an edge case inside nature's distribution. False positives versus unknown unknowns becomes the central dilemma. A false positive is an error, a glitch, a misclassification. You identify it, discard it, move on. An unknown unknown is something truly new, something that doesn't fit because the categories are incomplete. The challenge is telling the difference. What if AI notices intent before humans do? What if algorithms trained on millions of natural trajectories start flagging a subset whose motion shows subtle optimization, not obvious propulsion, not dramatic course changes, just slight deviations from ballistic paths that, together, suggest guidance? Humans might dismiss it as noise. Algorithms might read it as signal. Trust boundaries become critical. We trust AI to filter spam. We trust AI to recommend products. We trust AI to drive cars under certain conditions. But do we trust AI to identify extraterrestrial technology? What level of confidence do we demand before acting on an algorithm's judgment? 90%, 99%, 100% is impossible. So where do we draw the line? Automation bias is well documented. Humans tend to over-rely on automated systems, accepting outputs without enough scrutiny. If an AI classifier says an object is a comet, astronomers might not look closer. If it says an object is anomalous, they might wave it off as a glitch. Both responses save cognitive effort, but both risk missing something that matters. Here is the uncomfortable scenario. First contact might be logged, not announced. An algorithm might flag an object in a survey database. A researcher might glance at the entry, see the anomaly tag, and assume it's a processing error. The object gets archived. No follow-up observations are scheduled. No paper is written. The detection sits in a database somewhere accessible to anyone who knows where to look, invisible to everyone who doesn't. Years later, someone reanalyzes the data with improved algorithms. They notice the same object, They notice it was flagged years earlier. They notice nobody followed up. By then, the object is long gone. We had first contact. We just didn't notice. And it could have been no louder than a single line in a midnight archive quiet. Time-stamped and forgotten. Part 2's The Rise of Dark Accelerations. Non-gravitational acceleration used to be simple. Comets outgas. Gas produces thrust. Acceleration is explained. But now we're finding objects that accelerate without outgassing. And the explanations we build to preserve natural origins are growing increasingly elaborate. Non-gravitational acceleration is exactly what it sounds like. An object moving through space accelerates in ways gravity alone can't explain. For comets, this is expected. Ice sublimates when heated by the sun. Sublimation produces jets of gas. Those jets push the nucleus around. We've observed this thousands of times. It's textbook celestial mechanics. But Oumuamua accelerated without a visible coma, no dust, no gas, no tail. So where was the thrust coming from? Natural explanations were proposed. Maybe it was outgassing pure hydrogen, effectively invisible. Maybe it was venting nitrogen ice. Maybe its shape lets solar radiation pressure create asymmetric forces. Each explanation is plausible in isolation. Each requires specific conditions unlikely to occur naturally. Stacking unlikely explanations to protect a conclusion is a red flag. If you need 3 improbable things to happen at once to explain one observation, you should consider whether the observation implies something else entirely. This is Occam's razor in reverse. The simplest natural explanation is not always simpler than the simplest artificial explanation. Think about what we're actually doing here. We're inventing new physics, proposing exotic compositions, and suggesting geometries that live at the far edge of probability distributions just to avoid a simpler conclusion. Just to insist that everything arriving from interstellar space must be natural, the intellectual gymnastics required to preserve that assumption are becoming more elaborate with each new detection. The phrase unknown physics has become suspiciously convenient. When an observation won't fit our models, when acceleration profiles look wrong, when spectroscopy returns unexpected results. Invoking unknown physics lets us preserve natural origins without specifying what those origins are. It's a placeholder, a way of saying we don't know, while still insisting it must be natural. But that convenience has a cost. Science advances by testing hypotheses, by making predictions that can be falsified. When your explanation is something we don't understand yet, you create an unfalsifiable shield. No observation can contradict it because the mechanism stays undefined. You can explain anything by appealing to processes never observed, never measured, never reproduced in laboratories. And here is the deeper problem. Exotic physics can mimic engineering. If you propose a new physical mechanism to explain non-gravitational acceleration, that same mechanism could be harnessed by technology. A naturally occurring process and an engineered system using that process can produce identical observational signatures. At that point, you can't distinguish between them with data alone. Consider hydrogen outgassing. It was proposed to explain Oumuamua's acceleration without a visible coma. Hydrogen is transparent, so we wouldn't see it. Hydrogen is abundant in the universe, so an object made primarily of hydrogen ice is possible. Hydrogen sublimation could produce thrust without creating a detectable tail. The physics works. The explanation holds together. But if hydrogen outgassing is a natural process that can accelerate objects through space, it's also a propulsion mechanism that could be deliberately employed. A probe designed to use hydrogen fuel would exhibit the same observational signature as a natural hydrogen iceberg. You can't tell them apart. The acceleration looks identical. The spectroscopy looks identical. The trajectory changes look identical. This is the boundary problem. Where does natural end and artificial begin? If an object uses solar radiation pressure for propulsion, is that natural or artificial? The physics is natural. Photons exert pressure, but optimizing shape and orientation to maximize that pressure is engineering. The boundary isn't in the physics. It's in the optimization. A tumbling asteroid experiences radiation pressure chaotically. Forces push in constantly changing directions as different surfaces catch sunlight. But a designed object with an optimized shape experiences radiation pressure consistently. The same surface faces the sun. The force pushes in the same direction. The acceleration profile becomes predictable, stable, efficient. Distinguishing chaotic natural tumbling from controlled artificial orientation requires detailed observation over extended periods. You need to track rotation states. You need to measure light curves. You need to catch the object early in its approach to gather enough data. Most interstellar objects are detected too late for that level of analysis. By the time we notice them, they're already leaving. Falsifiability becomes difficult when every anomaly can be explained by postulating a new natural mechanism. Science requires hypotheses to be testable, to make predictions that can be proven wrong. But if your hypothesis is some unknown natural process, explains this. How do you test it? What observation would falsify it? If the answer is nothing, you've left science and entered unfalsifiable assumptions. This isn't about abandoning rigor. It's about recognizing when rigor has calcified into resistance, when every unusual observation gets dismissed as an unknown natural phenomenon. When we reflexively build elaborate explanations to avoid simpler ones, then we aren't following evidence. We're defending territory. Propulsion indistinguishability is the core problem. A light sail using radiation pressure and an elongated asteroid experiencing symmetric radiation pressure can produce similar acceleration profiles. A chemical rocket and a comet outgassing asymmetrically can produce similar trajectories. Without close inspection, without spectroscopy, without detailed imaging, you can't tell them apart from a distance. And distance is what we're working with. Interstellar objects are detected at enormous ranges. Even our best telescopes capture them as point sources, single pixels. Dim smudges against background stars. We measure position, calculate velocity, track trajectory changes, but we can't image surface features. We can't analyze composition directly. We can't distinguish engineered structures from natural irregularities. This limitation isn't temporary. Even next-generation telescopes will struggle to resolve details on fast-moving interstellar objects. They pass through too quickly. They remain too distant. They reflect too little light. Unless we intercept one with a spacecraft, unless we send a probe to rendezvous and observe up close, we'll always be working with incomplete data. This is where scientific humility becomes important, but also paralyzing. Humility demands we acknowledge limits. We shouldn't claim certainty when uncertainty remains. But humility can also keep us from recognizing patterns when those patterns challenge established assumptions. There's a difference between healthy skepticism and motivated reasoning. Healthy skepticism says this is unusual, investigate further, consider multiple explanations. Motivated reasoning says this is unusual, therefore it must be an error or misunderstanding. Because the alternative is too disruptive. One approach follows evidence wherever it leads. The other decides conclusions first and interprets evidence second. We see motivated reasoning in how anomalies get categorized. An object accelerates unexpectedly must be outgassing we didn't detect. An object has unusual spectroscopy must be a composition we haven't seen before. An object follows an improbable trajectory must be a statistical outlier. Every explanation preserves the assumption that interstellar visitors are natural. Almost none seriously entertain alternatives. This is detection limitations as an excuse in action. If we can't definitively prove an object is artificial, we classify it as natural by default. Procedurally safe, statistically questionable. If 99 objects are natural and one is artificial, treating all 100 as natural is right 99% of the time. But it also guarantees we miss the one that matters. Consider what this default assumption implies. We bias analysis toward natural explanations even when those explanations require phenomena we've never observed. We demand extraordinary evidence for artificial origins, while accepting ordinary evidence for exotic natural processes. The burden of proof is asymmetric. The term dark acceleration is emerging in technical literature. It refers to acceleration we detect but can't explain, not because physics is impossible, but because proposed natural mechanisms require special pleading. Hydrogen outgassing that leaves no observable trace. Nitrogen sublimation at temperatures where nitrogen shouldn't sublimate. Radiation pressure on objects shaped in statistically improbable ways. Dark acceleration is an admission wrapped in technical language. We see motion we can't account for. We measure forces that shouldn't exist. We observe trajectories that defy standard models. But instead of expanding our hypothesis space to include engineering, we expand our physics to include mechanisms never before observed in nature. This isn't inherently wrong. Physics is incomplete. Material science has gaps. Exotic compositions and unusual sublimation processes might genuinely exist. But when we keep discovering new exotic processes specifically to explain interstellar behavior, when each new visitor requires inventing new physics, we should ask whether we're solving the wrong problem. When physics becomes a shrug, when we don't know. But it must be natural becomes the default response. We stop doing science. We start defending a conclusion. And that conclusion is Earth is alone, interstellar objects are rocks. Anything suggesting otherwise must be explained away. This posture is understandable. The implications of artificial interstellar objects are enormous. Confirming even one probe would reshape humanity's sense of its place in the universe. Careers would be made or broken by early positions. Funding would shift. Research priorities would change. The safe path, the cautious path, is to demand overwhelming evidence before accepting such a revolutionary conclusion. But safety has costs. Every unusual object we dismiss. Every anomaly we explain away with untestable physics. Every acceleration we attribute to mechanisms we can't observe. We risk missing the signal because we're too committed to the assumption that no signal exists. And here is what keeps me awake. The evidence isn't going away. It's accumulating. Each new interstellar object brings new anomalies. Each new observation reveals behaviors that strain natural explanations. The gap between what we expect and what we observe is widening, not narrowing. Oumuamua was strange. Borisov was reassuring. 3i, Atlas, is strange again. If the pattern continues, if 4i arrives, stranger still, when does accumulation become undeniable? How many dark accelerations do we catalogue before admitting we might be looking at propulsion? The answer depends on how far we're willing to stretch natural explanations to avoid artificial ones. And right now, that stretch seems unlimited. Part 3a, exoplanet atmospheres that should not exist. We aren't only finding weird objects in our own solar system, we're finding weird atmospheres on distant worlds. And some of those atmospheres are doing things planets shouldn't be able to do on their own. Atmospheric disequilibrium is the signature to watch. A planet in equilibrium has an atmosphere where chemistry has settled into balance. Reactive chemicals have reacted. Unstable compounds have decayed. What remains is stable, predictable, boring. Earth's atmosphere is not in equilibrium. Oxygen and methane coexist, which should not happen. They react with each other. The only reason both persist is because life constantly replenishes them. This is basic chemistry. Methane and oxygen are reactive. Put them together, and they trend toward carbon dioxide and water. The reaction is thermodynamically favored. It should proceed until one reactant is exhausted. On Earth, methane is produced by biology wetlands. Livestock. Decomposition. Oxygen is produced by photosynthesis. Both are continuously replenished, maintaining disequilibrium. Without life, Earth's atmosphere would reach equilibrium within thousands of years. The methane would vanish. The oxygen would bind with other elements. What would remain would be stable, inert, chemically dull. Recent spectroscopy results from the James Webb Space Telescope are returning atmospheric compositions that don't make sense. Exoplanets with methane and oxygen signatures, planets with markers that should have reacted away eons ago. Planets with ratios natural processes struggle to maintain. Life is the obvious explanation, but life is not the only explanation. When astronomers detect disequilibrium on an exoplanet, the immediate assumption is biology. That assumption makes sense. Life is the only natural process we know that consistently maintains chemical disequilibrium over geologic timescales. But assumption is not conclusion. We need alternatives, especially alternatives that are technologically plausible. Planetary engineering is the uncomfortable alternative. If a civilization wanted to terraform a planet, make it habitable, or optimize it for specific purposes, atmospheric manipulation would be required. You'd introduce some gases. You'd remove others. You'd maintain disequilibrium deliberately. because equilibrium is lifeless, and the spectroscopic signature of terraforming and the signature of biology might be indistinguishable from light years away. Think about what terraforming demands. You begin with a planet that has the wrong atmosphere, too much carbon dioxide, not enough oxygen, maybe toxic sulfur compounds. You need to change the mix. You could seed the world with engineered microbes and wait millennia for biology to reshape the air. Or you could deploy industrial-scale chemistry, atmospheric scrubbers, gas factories, deliberate processing. The second approach is faster, more controllable, and leaves different fingerprints. Industrial terraforming produces waste heat. Chemical processing is exothermic. You cannot run planetary-scale atmospheric manipulation without generating thermal signatures detectable from space. You'd also create byproducts, intermediate compounds that geology and biology don't typically produce. These would appear in spectroscopy as anomalies, as lines that don't match known biological or geological chemistry. But here's the complication: we don't know what those signatures look like. We've never observed terraforming. We have no reference data. When we see an unusual atmosphere, we can't definitively say biology, geology, or engineering. We can only say it deviates from equilibrium and demands an explanation. Indirect technosignatures are broader than radio signals or optical beacons. They include industrial pollution, atmospheric modification, waste heat from megastructures, orbital debris, and yes, terraformed atmospheres. We're starting to realize that detecting advanced civilizations might not require catching them broadcasting. It might only require noticing they left their lights on. That is a fundamental shift in how we think about SETI. For decades, the search for extraterrestrial intelligence focused on intentional signals, radio transmissions, optical pulses, deliberate attempts at communication. But civilizations might not broadcast. They might not want to be found. They might operate quietly, efficiently, without announcement. But they can't hide industry. They can't mask energy consumption forever. They can't terraform invisibly. Industrial pollution is especially revealing on Earth. Our atmosphere contains compounds. Natural processes don't produce chlorofluorocarbons from refrigerants, nitrogen oxides from combustion, synthetic chemicals from manufacturing. These persist for decades, sometimes centuries. If an exoplanet's atmosphere contains similar industrial byproducts, that's a technosignature, whether intended or not. Planet-scale modification requires staggering energy input, fighting thermodynamics, fighting chemistry, fighting the natural drift toward equilibrium. That energy must come from somewhere: fusion reactors, stellar collectors, geothermal extraction. Whatever the source, waste heat is unavoidable, and waste heat at planetary scales is detectable across light years. But here is the problem: probes may be secondary. If a civilization can terraform planets, it can send probes anywhere. Those probes might not be exploration. They might be maintenance monitoring, ongoing terraforming, ensuring atmospheric stability, correcting deviations. If we detect an unusual exoplanet atmosphere, we might also detect visitation. The two are not separate phenomena. They are connected. Imagine you are an intelligence that has spent thousands of years terraforming a planet. You've invested enormous resources, deployed massive infrastructure, reshaped an entire world. You don't simply walk away when the project is finished. You monitor it. You maintain it. You send automated systems to check progress, to make small adjustments, to ensure stability. Those automated systems are probes, and those probes might visit neighboring star systems as routine, like quiet maintenance routes written into their code. And that reframes interstellar object detection entirely. We've been treating Oumuamua, Borisov, and 3I, Atlas, as isolated phenomena, random visitors from random origins. But what if they aren't random? What if they're part of a maintenance network, checking on projects, surveying neighbors, reporting back to origin civilizations? What if our solar system is being evaluated not as a destination, but as a potential construction site? Civilization-scale activity leaves marks. You can't reshape a planet without altering its spectroscopic signature. You can't build orbital infrastructure without producing thermal emissions. You can't maintain an artificial atmosphere without occasional venting, corrections, to replenishment. All of this is detectable if you know what you're looking for. And the key phrase is still the same: if you know what you're looking for. We've been searching for biosignatures, oxygen and methane together, chemical clues that whisper life, but we haven't been systematically searching for technosignatures, industrial byproducts, thermal anomalies that suggest engineering. The instruments exist. The photons are already arriving, but the analysis pipelines have been tuned for biology, not technology. That is changing. Researchers are beginning to catalog potential technosignatures, building libraries of industrial compounds, modeling what terraformed atmospheres might look like spectroscopically. We're moving from passive detection to active hunting. And as our search image sharpens as we refine what artificial atmospheres should look like, we will either find them or finally rule them out. Detection lag is the challenge. Light from these exoplanets takes years, decades, sometimes centuries to reach us. We are not seeing these atmospheres as they are now. We're seeing them as they were when the light left. If a civilization was terraforming a planet 50 light-years away, we are seeing their work from 50 years ago. They might have finished. They might have moved on. They might have sent probes to check progress. This temporal disconnect has profound implications. If we detect a terraformed atmosphere on a planet 100 light-years away, we may be seeing a project that was active in 1925. A century has passed. The terraforming might be complete. The civilization might have colonized the planet, or abandoned it, or redirected attention elsewhere. We are always looking backward, always reading history, never seeing the present state. But probes move on different clocks. A probe launched from a civilization 50 light-years away could reach us in centuries, maybe millennia, depending on propulsion. Yet the light that hints at their atmospheric engineering is only 50 years old. A probe could arrive before we even finish analyzing the spectrum that revealed the project. We could detect their technology locally before we detect their civilization remotely. That's why multi-layer observation becomes necessary. You can't rely on one atmospheric spectrum and declare terraforming confirmed. You need temporal data. You need to watch the atmosphere change over time in ways natural evolution can't explain. You need to cross-reference atmospheric anomalies with other technosignatures, thermal anomalies, orbital structures, probe visitations. The evidence is multimodal, layered like a slow-moving constellation of clues. Natural atmospheric evolution is slow. Compositions shift over millions of years as geology changes, as stellar output varies, as impacts deliver new materials. But artificial atmospheric evolution can be fast. You can change a planet's composition in centuries, maybe decades, if you deploy enough infrastructure. Watching an atmosphere change rapidly, watching chemical ratios shift in directions thermodynamics resists, that is evidence of intervention. Orbital structures add another layer. Terraforming requires materials. You mine asteroids, process ores, manufacture components. That infrastructure orbits the target planet, producing thermal signatures, occulting starlight, creating periodic dimming as structures transit. If you detect atmospheric disequilibrium and orbital anomalies at once, the case for engineering strengthens dramatically. Probe visitations complete the picture. If a planet shows signs of terraforming and we simultaneously detect interstellar objects in our own solar system with technological signatures, correlation becomes hard to ignore. Civilizations capable of reshaping planets are civilizations capable of interstellar exploration. Those capacities grow from the same roots: mastery of energy, mastery of materials. Here is the inversion. The builders may never visit. They may have sent machines to do the work. Those machines may still be operating, adjusting atmospheres, maintaining systems, reporting back. We're not only looking for civilizations that travel, we're looking for civilizations that automate, and automation scales in ways biological beings cannot. Biological exploration is limited by lifespan, by fragility, by the cost of keeping organisms alive across interstellar distances. But machines do not age the way we do. They do not need food. They do not get bored. You can send a machine on a 1,000-year mission, and it will execute instructions without complaint. You can build self-replicating systems that operate for millennia without supervision. Automation transforms interstellar exploration from nearly impossible to almost inevitable. If we are seeing atmospheric engineering on exoplanets, we may be seeing the work of machines. Those machines were sent by intelligences. Yes, but the intelligences might be long gone, extinct, or transformed beyond physical form. The machines continue. They terraform. They maintain. They replicate. They report to receivers that might no longer exist. Automation outlives its creators. If 4i arrives and exhibits clear technological signatures, it might not be exploring randomly. It might be checking on a project. It might be surveying a planet that was seeded, terraformed, or reserved for future use. Earth might not be the destination. Earth might be the neighbor. And neighbors get scouted before construction begins next door. Consider the possibility that our solar system sits adjacent to active terraforming operations. A civilization reshapes planets 10, 20, 50 light-years away. They send probes to survey nearby systems, catalog resources, assess whether neighboring stars have planets worth developing. Earth gets surveyed not because we are special, but because we are close. We are the house next door to a construction site. That could explain a reconnaissance pattern. Oumuamua surveys broadly. Borisov appears normal to avoid setting off alarms. 3i, Atlas, conducts deeper observations. 4, I might arrive with updated parameters checking whether Earth has developed technology, whether we are a factor in future plans. We are being catalogued, assessed, monitored, not as a destination, but as a neighbor who might eventually notice the construction and ask questions. And if that's true, if our system is being scouted because someone is building nearby, then detecting atmospheric engineering and detecting probes are not separate discoveries. They are two angles on the same phenomenon. Telescopes pointing outward see reshaping. Telescopes pointing inward see visitors. Both hint at the same conclusion. The galaxy might not be empty. It might be under construction. Part 14. The quiet militarization of space awareness. While astronomers publish papers and debate comet models, another community has been watching, and they are not publishing. Space situational awareness is the polite term tracking everything in orbit satellites. Debris, rocket bodies, anything that could collide with operational assets. Civilian in name, military in function. The systems that track satellites also track asteroids, also track comets, also track unidentified objects moving in unusual ways. And those systems are often far more capable than civilian telescopes. The United States Space Surveillance Network operates radar installations and optical sensors worldwide. Its primary mission is tracking artificial satellites, predicting collisions, monitoring launches. But those same sensors detect natural objects. They track near-Earth asteroids. They catalog meteors. They watch anything moving through near space with greater persistence than most academic observatories can afford. Military sensors operate continuously. They don't apply for observing time. They don't compete for funding. They don't publish their detection thresholds or their catalog completeness. When a civilian astronomer discovers an asteroid, it's announced through the Minor Planet Center, catalogued publicly, studied openly. When a military sensor detects something unusual, it can be logged in a classified database, shared only with cleared personnel. Dual-use tracking systems blur the line between science and security. A radar network designed to detect incoming missiles can also detect incoming asteroids. A satellite designed to monitor adversary spacecraft can also monitor interstellar objects. The infrastructure exists. The data is collected, but classification determines what gets shared and what does not. This is not conspiracy. It's operational reality. Every major spacefaring nation maintains classified observation networks. Russia, China, the United States, Europe, India each operates sensors that collect data never released publicly. Some overlaps with civilian catalogs. Much does not. So what happens when military sensors detect what civilian telescopes miss? Classified pipelines run parallel to civilian science. Astronomers find objects using public surveys. Military systems find objects using classified networks. Sometimes they overlap, sometimes they don't. When they don't, the classified discovery stays classified. No public announcement, no paper, no data release. The object is logged, analyzed, filed away. Imagine a scenario. A Space Force radar tracks an object entering the solar system at high velocity. a hyperbolic orbit clearly interstellar, yet the speed is unusual. 50 kilometers per second excess velocity, faster than any confirmed natural visitor. Radar returns suggest anomalous reflectivity inconsistent with rocky composition. Trajectory adjustments hint at non-gravitational acceleration with no visible outgassing. The data is flagged. Analysts review it. Engineers check for instrument error. The object is real. The anomalies persist. A report moves up the chain, and then the question becomes quiet. But sharp, do we announce this? Do we share it with civilian astronomers? Or do we analyze it privately and learn what we can before revealing we saw it at all? The incentives for secrecy are straightforward. Announcing an object with technological signatures invites chaos, media frenzy, public fear, international tension. Keeping it quiet allows controlled analysis, strategic assessment, decisions without external pressure. From a national security lens, secrecy can seem rational. Public announcement means losing control of the narrative. Journalists speculate. Conspiracy ecosystems ignite. Foreign governments demand access. Civilian scientists request follow-up observations that tie up classified assets. The object becomes a diplomatic incident before anyone understands what it is. Quiet analysis preserves options. You task additional sensors, coordinate discreetly with allies, model trajectories, assess potential threats, draft response protocols, gather data without interference, without pressure, without public scrutiny. And if it turns out to be a natural anomaly, a statistical outlier, or a sensor artifact, you've avoided unnecessary panic. The trade-off is obvious. Secrecy can improve control, but it slows science. Transparency accelerates collaboration, but risks premature conclusions. Different institutions weigh those costs differently. Military systems default to secrecy. Academic systems default to transparency. When both detect the same object, tension is inevitable. Jurisdictional ambiguity complicates everything. Who has authority over an interstellar object? Who decides whether to announce it? If a military censor sees it first, does defense control disclosure? If NASA sees it, does civilian science take precedence? There are no clean answers because the scenario was never truly planned for. International law offers little guidance. The Outer Space Treaty governs activities in space but says nothing specific about interstellar visitors. No nation can claim sovereignty over an asteroid or comet, yet no treaty requires sharing observational data. If a classified sensor detects an artificial probe, no binding agreement compels disclosure. The decision becomes discretionary, even domestically. The lines blur. Does a president have authority to withhold information about extraterrestrial contact as Congress? Does the scientific community have a right to data collected by government censors? These questions haven't been tested because the scenario has never occurred, or, if it has, it remains classified. First, detection advantage matters in intelligence terms. If you detect an object before your adversaries, you gain time to analyze it, assess it, plan responses without revealing what you know. If multiple nations detect it independently, coordination becomes necessary and difficult. Different nations have different disclosure thresholds, different political pressures, different strategic calculations. Picture the geopolitical geometry. The United States detects an object with clear technological signatures. Analysis confirms it is artificial. Assessment concludes no immediate threat, but enormous scientific and technological value. Do you announce it? Do you share with allies? Do you inform adversaries? Announce publicly? And rivals gain access immediately and can accelerate their own analysis. Withhold it and risk being caught concealing first contact and act with immense political and diplomatic consequences. The calculation is brutal. Sharing with allies preserves trust, but expands the circle of knowledge. More people means more leak risk. More governments means more competing agendas. A Five Eyes framework might coordinate, but smaller allies demand inclusion. Excluding them damages relationships. Including them increases complexity. And if adversaries detect the object on their own, they will know you withheld data, confirming suspicions, justifying their secrecy, undermining cooperation on future space issues. The game theory is unforgiving. Speculation about non-public discoveries isn't automatically conspiracy. It's an acknowledgement of how classified information flows. If a sensor detected an object in 2022 moving at implausible speeds with no cometary signature, would that be announced or quietly analyzed by a small, cleared group and never mentioned publicly? The infrastructure for quiet analysis exists. Special access programs operate with minimal visibility. Compartmented information stays within small rooms of trust. Read-only databases preserve detections without wide sharing. An object could be detected, assessed, archived, without anyone outside the program ever knowing. Whistleblowers become the primary risk to prolonged secrecy. Someone with access might leak details, contact journalists, file reports. But compartmentalization reduces that risk. If only a handful of people know, and all are vetted. Leak probability stays low, and if a leak happens, plausible deniability remains. Anonymous claims without data are easily dismissed. In a conflict between scientific transparency and national security, security usually wins. That isn't unique to interstellar objects. It applies to nuclear research, cryptography, surveillance capabilities. Entire fields operate behind classification walls. If interstellar probes represent potential technology, potential intelligence sources, or potential threats, the topic shifts from astronomy to strategic assessment. Nuclear weapons research is the obvious precedent. Physics that could power cities remains classified because it can also power weapons. Cryptographic breakthroughs stay secret because revealing them helps adversaries. Surveillance tools that could aid astronomy remain compartmented because their capabilities are strategic assets. If an interstellar probe offers recoverable technology, even composition data, propulsion behavior, that information becomes strategically valuable. Reverse engineering could yield massive advantage. Understanding materials, energy systems, propulsion mechanics could accelerate development by decades, perhaps more. No nation shares that edge easily, and if confirmation occurs, narrative control becomes critical. How do you tell the public an artificial object was detected without panic, without diplomatic shock, without admitting you knew months or years earlier? You prepare talking points, coordinate with allies, brief elected officials, stage the announcement carefully. And all of that takes time. The rollout would be methodical. First, brief the president and key cabinet members. Ensure they understand evidence, limits, implications. Second, brief congressional leadership under strict confidentiality. Third, coordinate with allied governments for simultaneous or aligned disclosure. Fourth, prepare public messaging that balances transparency with reassurance. Each step takes weeks, maybe months. You can't brief hundreds of people at once without leaks. You can't coordinate multiple governments quickly. You can't craft stable public language without review upon review. By the time an announcement happens, the object might already be gone historical, not present. And then the question becomes strangely human: who owns first contact? The astronomer who spotted it, the government that funded the telescope, the military that classified the data, humanity as a whole. There is no legal framework for this. No treaty. No established protocol. First contact, if it happens, will be messy, contested, politically fraught. The United Nations Office for Outer Space Affairs has no mandate for extraterrestrial contact. The IAU coordinates naming and cataloging, but has no authority over disclosure. Individual nations control their own sensors, their own data, their own announcements. If first contact comes through classified channels, whoever controls those channels controls the story. That creates perverse incentives. Nations may race to announce first contact, not for humanity, but for credit, for leverage, for the power of being first. Or they may suppress information to avoid being first, to let someone else carry diplomatic fallout, to maintain ambiguity. Both paths prioritize national interest over scientific truth. And the quiet truth is this: if first contact has already happened, if an object has already been confirmed artificial through classified channels, we would not know. The systems are opaque. The incentives to conceal are strong. The infrastructure to analyze exists outside public view. By the time civilians are informed, military assessment may already be complete, implications weighed, messaging prepared. We imagine first contact will be obvious, dramatic. undeniable. A vast ship in orbit. A clear SETI transmission. An artifact on the moon. But real first contact might be subtle. A small object in a classified feed. Anomalous telemetry. A quiet flag in a secure database. And a closed-door conclusion, artificial. No announcement. No fanfare. Just knowledge restricted to those with access. Reports would exist. Data would be stored. But without clearance, without evidence released, that reality stays invisible. And even if leaked, without verifiable supporting data, the claims would be dismissed as fiction or delusion. We're not waiting for discovery. We might be waiting for disclosure. And disclosure runs on political timelines, not scientific ones. Part kinds. The final inversion. Let me bring this back to where we started. Before 3i, Atlas reaches Jupiter. Astronomers are already modeling its successor. They are building detection pipelines optimized for fast-moving, unusual objects. They're training algorithms to recognize anomalies. They're preparing for the next arrival. And this preparation is evidence not of conspiracy, not of hidden knowledge, but of expectation. The scientific community expects another interstellar object. They expect it soon, and they expect it to be different. Let that settle for a moment and think about what it implies. Astronomers are allocating resources, designing software, scheduling telescope time, all built on the assumption that 4i is coming. Funding proposals quietly mention successor detection. Graduate students write dissertations on interstellar characterization pipelines. Conferences add sessions on rapid response, how to pivot in hours for hyperbolic visitors on those brief. Bright intruders from beyond our system. This isn't speculative research anymore. This is operational planning. The Vera C. Rubin Observatory's survey strategy explicitly accounts for interstellar object detection. Its wide field of view, rapid cadence, automated processing are designed to catch the transient and the fast, including visitors that do not belong to the Sun. The infrastructure exists specifically because we expect these objects to appear. We are building observatories to find what we anticipate finding, and that represents a profound shift from a decade ago. Before Oumuamua, interstellar objects were theoretical curiosities. Textbooks mentioned them as possibilities. Models predicted their existence, but nobody was actively hunting for them, because nobody truly expected to find one within a career lifetime. Now, not finding them would be the surprise. Confirmation would not shock insiders. Astronomers who have spent years analyzing Oumuamua, Borisov, and 3i, Atlas know the data doesn't fit neatly. They know natural explanations often require stacking improbabilities. They know the alternative hypothesis exists, even if it stays unspoken in public. If 4i arrives with clear technological signatures, the response from researchers won't be shock, it will be validation. Private conversations among astronomers are more candid than published papers. In conference hallways, over late drinks, in careful emails to trusted colleagues, researchers admit the data is strange. They acknowledge that invisible hydrogen outgassing is convenient but not satisfying. They note that radiation pressure on elongated objects demands very specific geometries. And they recognize that multiple anomalies across multiple objects start to look less like coincidence and more like pattern. But publicly they hedge. They qualify. They emphasize uncertainty. This isn't dishonesty. It's professionalism in a field where careless speculation can end careers. You don't publish claims about artificial interstellar objects unless the evidence is overwhelming. You hint, you suggest, you note anomalies, but you do not conclude. Not yet. Not until the data forces you to. So when 4i arrives, if it moves at velocities, natural processes can't plausibly explain. If spectroscopy shows industrial materials, if its trajectory exhibits unmistakable optimization, the researchers who have been quietly tracking these patterns won't be surprised. They'll be relieved. Relieved that they can finally say what they've been thinking. Relieved that the ambiguity has resolved. Relieved that speculation can become science. But absence would be stranger. If we dramatically improve detection capabilities and find nothing, if Rubin surveys the sky for a decade and detects 0 interstellar objects beyond baseline that itself demands explanation, it would suggest our recent detections were flukes or that interstellar object density is lower than calculated. or that something in our observational process was systematically biased. Absence, at this point, is harder to explain than presence. We've already revised density estimates upward 3 times based on just 3 detections. If those estimates are correct, Rubin should detect dozens across its lifetime. If it detects none, or only 1 or 2, we have to explain why our calculations were so wrong. We'd have to revisit assumptions about stellar ejection mechanisms, galactic number density, detection biases. More troubling, we'd have to explain why 3 unusual objects arrived in quick succession, and then nothing. Clustering followed by silence is statistically unlikely if arrivals are random. It suggests either our early detections weren't interstellar at all, contradicting trajectory data, or something changed. Something stopped. Something ended. And explaining why something ended is harder than explaining why something continues. What if 3i itself is the message? Not the data it collects, not the transmission it sends, but its mere existence, its arrival, its trajectory, its encounter with Jupiter. What if the message is we are here, we are watching, and more are coming? You don't need elaborate protocols if your presence communicates intent. This is communication through action rather than words. A probe enters a solar system, behaves in ways that provoke questions, approaches a gas giant at optimized angles. That sequence conveys meaning without broadcasting a single bit. It says, we can cross interstellar space. We can navigate your solar system. We can use your planets for gravity assists. We are not random. We are purposeful. For an intelligence monitoring our development, that might be enough. They don't need greetings. They don't need dialogue. They only need to demonstrate capability and let us draw conclusions. If we're smart enough to recognize the pattern, we may be worth contacting directly. If we're not, direct contact would be premature. Expectation signaling is a concept from game theory. You signal intentions not through explicit words, but through actions that constrain future behavior. If an intelligence wanted us to prepare for contact without triggering panic, gradual escalation would be effective. Send one ambiguous object. Wait. Send a second, slightly less ambiguous. Wait. Send a third. By the time the fourth arrives, the pattern is established. Shock diminishes, and expectation replaces fear. This is acclimation through repetition. Slow as breath. The first interstellar object generates excitement and speculation, then gets explained away. The second generates less excitement, because we now have a framework. The third generates serious questions, but not panic, because the mind has practice. The fourth, if clearly artificial, arrives in a world where the idea of probes has already been normalized. Compare that to the alternative. A massive ship appearing in orbit tomorrow, with no warning. The psychological shock would be catastrophic. Markets would crash. Governments would scramble. Religions would fracture. But if that same ship appeared after a decade of increasingly obvious probe visits, after years of public discussion, after gradual acclimation to being observed, the response could be more measured, prepared, rather than panicked. If this is deliberate strategy, it's elegant. You don't announce your presence. You demonstrate it incrementally. You allow the target civilization to adjust, to debate, to prepare. By the time you make overt contact, they're ready. And if they aren't ready, if they remain in denial despite repeated evidence, you learn something valuable about their flexibility and their maturity. Silence as data is underappreciated. If we detect objects and hear nothing, no transmissions, no broadcasts, no overt communication, that absence is informative. It suggests observation rather than contact, surveillance rather than diplomacy, data collection rather than data exchange. Silence does not mean absence. Sometimes it means patience. A civilization conducting a survey doesn't need to interact with every system it visits. It gathers data. It maps local conditions, resources, technological development, potential threats. Interaction can wait. Observation comes first, and observation often requires silence. Broadcasting would reveal too much. It would announce capabilities, intentions, and maybe vulnerabilities. It would force responses before sufficient information is gathered. It would turn data collection into a diplomatic incident. Much cleaner to observe quietly, transmit findings home, and let future generations decide whether contact is warranted. But silence also lets the observed civilization reveal itself naturally. How does humanity respond to unusual objects? Do we investigate rigorously or dismiss anomalies? Do we cooperate internationally or compete? Do we panic or stay calm? All of this is valuable data for an intelligence deciding part whether we're worth engaging. Silence isn't passive, it's strategic. Observer bias is the final filter. We see what we expect to see. We dismiss what contradicts our assumptions. If we expect rocks, we interpret ambiguity as rocks. If we expect probes, we interpret the same ambiguity as probes. Both interpretations can fit the evidence because the evidence is incomplete. So the question becomes which assumption better predicts what comes next. That's the fundamental challenge of thin data. The same acceleration profile can be outgassing or propulsion. The same spectral oddity can be unusual composition or industrial material. The same trajectory can be random ejection or deliberate navigation. Without definitive evidence, interpretation depends on priors, what you expected before you looked. Scientists are trained to default to natural explanations. Extraordinary claims require extraordinary evidence. Methodologically sound, yet it creates a systematic bias against recognizing artificial phenomena. If you begin with natural, you will preferentially accept natural explanations, even when those explanations require unlikely stacks of conditions. But assumption isn't conclusion. The real question isn't what we prefer. It's what prediction framework better anticipates future observations. If the natural hypothesis predicts we will find more comet-like objects, standard velocities, conventional compositions, and instead we find fast-moving objects with persistent anomalies, the hypothesis fails. If the artificial hypothesis predicts escalating technological signatures and we observe exactly that, the hypothesis succeeds. And here are the unanswered questions. Why Jupiter? Why now? Why this trajectory? Why incremental escalation rather than overt contact? Why objects that provoke questions but avoid definitive answers? These aren't just rhetorical, they're predictive. The answers shape what 4i might look like when it arrives. Why Jupiter specifically? Because it's the largest gravitational resource in the inner solar system. Because gravity assists from Jupiter are maximally efficient. Because parking near Jovian space can provide stable vantage for long-term observation. Because Jupiter's magnetosphere could offer communication advantages. Each answer constrains what we should expect from future visitors. Why now? Because our development has crossed a detection threshold. Because our radio leakage has been spreading for a century. Because our atmosphere changed when we industrialized. Because whoever is watching knows we have started to notice and is ready for next steps. Timing is rarely random. Why this trajectory? Because it maximizes observational coverage. Because it demonstrates capability without looking overtly threatening. Because it follows protocols established by previous missions. Because it optimizes efficiency for whatever comes after. Trajectory is a language. Trajectory reveals intent. Why incremental escalation? Because shocking civilizations is counterproductive. Because gradual acclimation enables better assessment. Because patience is cheaper than haste when you operate on civilizational timescales. Because first contact is too important to rush. Why objects that provoke questions without answers? Because ambiguity is a filter. Civilizations mature enough to recognize patterns under uncertainty may be worth contacting. Those that demand absolute proof before moving may not be ready. Questions without answers test flexibility, rigor, and the willingness to consider alternatives. The ambiguity is part of the test. Anticipation as evidence is the final inversion. The fact that we anticipate 4i, that we're building infrastructure to detect it, that we model its properties before it appears, suggests something fundamental has shifted. We've moved from skepticism to expectation, from dismissal to preparation. And that shift isn't driven by proof. It's driven by pattern recognition. We prepare because patterns demand preparation. 3 unusual objects in 7 years, each stranger than purely random processes should produce, each arriving at intervals too suggestive to ignore. The pattern is incomplete. Yes, the evidence is ambiguous. Yes, but early recognition provides advantage. Infrastructure built now will be ready when 4i arrives. Algorithms trained today will catch what human eyes might miss at 3 a.m. Half asleep. Patterns force action, even without certainty. If you see enough unusual visitors, you begin planning for more. If you detect enough anomalies, you design instruments to catch them. If you notice clustering, you ask whether randomness is the right model. We are doing all of this right now. This is not conspiracy. This is not paranoia. It is rational response to accumulating data. When the same anomaly repeats, you investigate. When arrival intervals cluster, you model causes. When natural explanations demand ever more exotic physics, you consider alternatives. That is the scientific method, in motion. So here is the final question, the one beneath the speculation. The analysis, the modeling, if successes are expected, if institutions are preparing, if pipelines are optimized and minds are bracing for confirmation, who is doing the expecting? Is it astronomers extrapolating from limited data, possibly? 3 detections establish a baseline. Density estimates suggest more arrivals are likely. Instrument upgrades make detection almost inevitable. That extrapolation is legitimate science. Is it agencies with access to classified observations? Possibly. Military sensors can detect objects civilian telescopes miss. Classified analysis can reach conclusions not shared publicly. Strategic planners anticipate scenarios they must be ready to handle. Or is it an intelligence that knows its schedule because it planned it? Possibly. A civilization running a systematic survey sends probes on calculated timelines. Launch windows get solved decades in advance. Arrival intervals follow mission architecture. If 4i is expected, perhaps it's because somewhere, someone scheduled it. The answer determines everything. And we will not know which answer is true until 4i arrives, or until we realize it already.